energy in general you do understand is basically the capacity or the ability to do work. This is very different from what we have been doing so far, where in motion or forces we were majorly talking about the various situational numericals. Chemical energy, so again you have an idea of what it is, but still just the basic definition. Alright, so electromagnetic sound and other waves. So you do understand, electromagnetic waves. So light, you might have called it an electromagnetic wave. Hello students, welcome to this second class of the unit Energy, Work and Power. So if you remember, in the first class we have talked about energy in general and the two classification of energy, that is energy stored and energy transferred. So in that particular class we have talked about energy stored and the various types of energy. So in this class our focus would be on energy transfer, and we will also introduce the concept of work. Okay, needless to remind you that you can only watch the second class, you can only, this class will only make sense to you if you have already watched the first class. So if you haven't done that, then go back to that particular video and then start with this class. Alright, so without wasting any time further, I think we shall start. So the first thing is different ways to transfer energy. So now we have talked about this, that we have energy in one form. Let's say we have energy right now in the form of chemical energy. We are having that ability to do work. Now let's say I wish to provide this pen with a kinetic energy. Just take that as an example. So I will throw this pen, right? So what is happening while I'm doing that? So I am basically applying a force and causing this energy to get transferred to the pen in the form of kinetic energy, right? So can we relate with this now, that we can transfer energy from one body to another or one system to another by applying force? Take for example weightlifting. So when you're doing weightlifting, what are you doing? You're pulling the dumbbells up, right? So you're providing them with potential energy, maybe a bit of kinetic energy, but for that you need force, right? So by applying force. Second, by heat transfer. So as you remember, in the last class we have talked about that, when you have two iron bars, one in the refrigerator and the other at the gas burner, and you bring them in contact, then basically the energy from the hotter bar gets transferred to the colder bar. So what is happening there? That is basically a transfer of thermal energy, right? So that's what we are talking about, heat transfer. So heat is being transferred, that means energy is being transferred, right? So you can take n number of examples here. You go out in the sun and there also, heat strikes you. That means you are gaining energy, your body temperature is rising. That is also because of heat, right? And there can be another way of looking at it, by the help of radiation, right? So radiation, you do understand, electromagnetic waves precisely are called radiation, which consist of many electromagnetic waves like visible light, infrared light, ultraviolet light. All these are called radiation, right? So when these radiation are transferred, or when these radiation travel from one point to another point, they do carry energy with them. So that is another way of transferring energy, and it is most important for us, at least, because we are gaining all the energy from the sun thanks to radiation. So radiation is the agency which is causing the nuclear energy of the sun to get transferred to the earth, and then all the other forms of energy are actually making sense. But the ultimate source of energy mostly is sun for us. So you do understand that all that is happening just because of radiation, right? Next is electric current. So you do understand that electricity is the most versatile form of transferring energy. Think about a fan, think about a tube light, think about a bulb, think about a robo. All these cases, you have electrical energy being converted to some other form of energy. So if the energy is coming to us with the help of wires, with the help of power plants. So all that transfer is happening because of electric current, right? So this stored energy here in the battery in the form of chemical energy is being given to the bulb in the form of heat energy or light energy, but all that is possible because there is current in the wires. So if this current is there, then that energy gets transferred from the battery to the bulb. So just to give you a brief, this is what are the different ways or the major ways of transferring energy. So we have talked about energy. Now we are talking about energy being transferred from one place to another. Just quickly write all these things and then we move forward. Alright, so next is conservation of energy. So it's obviously the follow-up thing. When we say energy is being transferred, that obviously implies someone has a debit and the other system has a credit of energy, right? Can we call it like that? So someone has lost energy and the other system has gained energy, and we can say there is a transfer of energy. It might look like for someone who has gained energy, that energy is created, but is it true? Can energy be created? No. So if you have gained energy, what is the correct word? Energy is not created. If I throw this pen has not, the kinetic energy has not been created. What would you say? It has been transferred. My chemical energy of the food has been converted to kinetic energy of the pen thanks to the force that I apply, and then it is basically a credit debit thing. So I have lost some energy and the pen has gained an equal amount of energy. So my loss of energy is equal to the gain in kinetic energy of the pen. So overall, if you combine both of us as one system, is there any change in energy? Answer is no. No energy is being changed. Energy is only getting transferred. That's what we are wanting to explain. The principle of conservation of energy states that energy can be created or cannot be created. Sorry, cannot be. So cannot be created or destroyed. It can be converted from one form to another or transferred from one body to another. The total amount of energy will always remain constant. So the total energy will never change for any isolated system. Maybe the earth is gaining energy, but then the sun is losing energy. So if we combine sun and earth as one system, then whatever is the loss by the sun on the earth is equal to the gain of thermal energy or any form of energy by the earth. So someone's loss is someone's gain is what we are talking about here. And you have n number of examples. Let's say this car is sloping down, like it's going through a slope and it's falling like this. Then what do you reckon? So you would say it had some potential energy, and when it is now moving and going down the hill, then it is gaining kinetic energy. Can you relate with that? So it will gain speed, it will gain kinetic energy, but potential energy is being lost, and similarly kinetic energy is being gained, and we can say an equivalent kinetic energy is being gained. So potential energy lost and kinetic energy gained. But all that is perfectly true, that this loss is equals to this gain if we ignore air resistance, all right, or if we ignore friction, solid friction between the tires or the wheels and the road. Because you do understand that when this is moving, the wheels are going to rub against the road, or they will roll over the roads. Then what is going to happen? Some heat will also be produced. So if you go by that sense, then you should always write potential energy lost is equals to kinetic energy gained plus heat energy gained or thermal energy gained by the wheels and the road particles, right, or the air particles. But if we mostly ignore this portion of energy, then we can say that kinetic energy gained is exactly equal to the potential energy lost. That is obviously the case. Same is pendulum. We have talked about pendulum in the previous unit. So this is called its extreme position, and this is like its mean position. So imagine you leave the pendulum from one position and it starts oscillating, then we would like to say that whatever height it has lost, of course it is losing height. Can you not imagine that pendulum when taken, let's say, in a gravity free space and you leave it here, will it ever come back? Will it have a tendency to come back to the mean position? No. So this is being brought back to the mean position thanks to gravity. So this gravity, so when it travels from extreme, to mean, then you do say that potential energy is getting converted to kinetic energy. But on the contrary, when you're going from mean to extreme, again that conversion is happening and kinetic energy is converting to potential energy. So vice versa is happening. But then you would say that if there is an energy conservation like that, then why would the pendulum ever stop? It is like always a conversion of kinetic to potential or potential to kinetic. But you do understand that this is a very ideal case where we have ignored air resistance. But if air resistance is also there, then obviously this conversion cannot be true, and there is always some energy diversion in the form of thermal energy of the particles of the pendulum and the air. And that is why every time pendulum oscillates, some energy gets into that portion and this energy keeps on diminishing, and ultimately the pendulum will come to a complete rest, right? So that is how you understand energy conservation. But if you don't take into account the thermal energy lost, then we can say that it's interconversion between kinetic and potential. Sometimes we combine them and call that as mechanical energy. What do we call that? Mechanical energy. Kinetic plus potential combined is called mechanical energy. So thermal energy is lost, and that is why we can say that mechanical energy cannot remain conserved. But if there is no air, it is free space, right? There is no air particles like on the moon, then you can say mechanical energy will always remain conserved. I hope you are able to understand. Okay. Next you can talk about this as well, where you have a hammer and you strike the nail. So when you do that, you convert your food's chemical energy into the gravitational potential energy, and when you strike it, then again that's converting to kinetic energy. But when it hits it, finally it converts into sound. Of course there is a huge sound, and thermal energy, because ultimately when you strike the nail will pass into the this wooden thing, and some form of energy is always in the form of thermal energy of the nail and the wooden board, right? So that is the case. I hope you are able to understand conservation of energy, which is very relatable. You can copy down the important stuff and then we move forward. All right, the next one is what we are going to talk about. These are the Sankey diagrams, where we are wanting to talk about these diversions of energy that we were just discussing, right? So we have taken this example of rocket propulsion, where a rocket is being fired, and you do understand that there is huge amount of fuel, there is huge amount of stored energy in the form of chemical energy, some kind of fuel that we burn. And what happens is, once that fuel burns, this chemical energy starts converting into many forms. Let's talk about one by one each of them. Sound energy. Of course, there is a huge roar when the rocket it moves. Then light energy. Of course, there is fire, there is huge amount of light being produced, heat being produced, huge amount of heat. Can you relate with this? Heat portion is quite, so that is what we are trying to do in the Sankey diagrams. We are also wanting to show the diversion, the component, the percentage, the portion with the help of thicker arrows. Then this was the chemical energy. Very small amount of it is in the form of sound. Then light is a little more than that. Then the huge amount goes into the thermal energy. Of course, there is huge amount of heat being produced. Then gravitational potential energy. Of course, the rocket starts rising, so there is a gravitational potential energy component, and since it's rising, it's gaining speed. It started off from rest, So it's gaining speed, it's gaining kinetic energy. So that is there as well. So almost like equal being shown here, but this might be a little different. But what is, important to observe here, that like this is what we want from a rocket, right? We just want it to just rise in height and gain speed. So these all three in a way like are not desirable. Like this is not what we want from a rocket. We just want it to lift off and go. So in a way these three are a loss of energy in that sense. So energy is not lost, but it is like, for us this is not useful energy. This is the useful energy. That is what defines efficiency of anything, right? The useful energy output to the total energy input, that is the fractional efficiency. And if normally you express it in percentage, then you multiply it by 100. So if you talk about this particular situation, then the useful output energy would be kinetic energy, right, and potential energy. So let's do a calculation quickly. Hypothetically, let's assume that this is okay. Let's not do that calculation here, but we can just assume that for reference this is like, let's say 100, right? So let's say 10 out of 100 parts, 10 part goes into this, whatever the unit is. Okay, let's say 20 goes into this, and let's say 40 goes into this. Okay, and then let's say 20 and or let's make this, let's say 30. Okay, so this is 30 plus 20, 50 plus 10, 60, and let's make these two as 20, 20 as well, right? So what is the efficiency then? So you would say that out of these 100 portion that we have spent, 10, 20 and 30, this is a waste for us, this 60, and the useful output energy is only the 40 part. So we can write this as 40 over 100 into 100, so it's like 40%, right? So this is just to give you an idea that how this accounts for the efficiency, right? So yeah, so that's about Sankey diagram. I'll take one more example to make you understand this, and then we move forward. All right, so let's take another example very quickly. So this hammer thing that I was talking about. So you spend some energy, let's say you spend chemical potential energy of 50 joule, and out of that 50 joule, let's ignore the air resistance almost. So you gain what? Potential energy first. So that's what it's showing, that you gain like potential energy, but before that you bring this in motion. So that's like kinetic energy, but then ultimately that converts to potential energy. So there is no loss here. So it's consecutive conversion. Now after this conversion is the Sankey diagram. Now what happens is, as soon as you strike the nail, what is happening? 5 joule is being lost in the form of thermal energy. Let's say 10 joule is being lost in the form of sound energy, and the remaining is again intact in the form of kinetic energy when you strike the nail, right? So what should be the efficiency then? So your sole purpose was to give it kinetic energy to the nail and stuff like that. So the efficiency is going to be useful output, useful energy over the total energy, right, times 100. So that would be, in this particular case, is 35 over 50 into 100. So that's like 70%, isn't it? That's like 70%. You can understand that. So that's about the Sankey diagrams. We will draw many Sankey diagrams when we will discuss the previous year questions, so that you can relate with more such situations, and you would be able to handle any new questions coming your way. Copy this down, then we move forward. All right, so now we have a question based on conservation of energy. Let's do this one. A 1.5 kilogram flower pot accidentally falls from a height of 30 meters, all right, that's quite huge, towards the ground. What is the gravitational potential energy of the flower pot before the fall? So by some accident this flower pot is falling. So the gravitational potential energy before the fall, we know the formula is mgh, all right, that's mgh. h. Now what is the mass? Mass is 1.5 kilogram, g has to be taken as 10 and h is like 30, alright. So this is going to be 15 times 30, that is 15 times 30, that's 4500, 450. 15 times 30 is going to be 450 and the unit, don't forget, that's joule, right? Next, speed of the flower pot just before it hits the ground, assuming negligible air resistance. So if there is no air resistance, we do understand that whatever was the potential energy gets converted into kinetic energy. Following, conservation of energy. So what will we write? Because of conservation of energy, we can write that whatever was the potential energy is equal to the gained kinetic energy. So since we know that it was 450, straight away let's put the value, that is equals to half times m is like 1.5 times v square. So let's do this calculation. This is 900 divided by 1.5, that's 600, square root the answer. Alright, so I am getting v as 24.5, alright, meter second inverse. So that's the speed, thanks to the fact that we do know that the potential energy is being converted to kinetic energy. So that is how you can also calculate the speed. Before this, you were always using equations of motion or concepts of acceleration and stuff like that to calculate speed, but here altogether it's a different approach where we are calculating speed using the fact that potential energy is being converted to kinetic energy. I will wait, you copy this down, then we move forward. Alright, next one. A car burns 4 into 10 raised to the power 6 joule of fuel energy. It gains 1.5 into 10 raised to the power 6 joule of kinetic energy while riding up a slope and gaining a potential energy of this much joule. How much energy transfers away in the form of thermal energy? So this is a practical question that we do know that, you know, input energy because of the fuel, right, is equal to the kinetic energy component, potential energy component plus thermal energy, right? So that thermal energy is because of the friction, air resistance, whatever you may call it, or fuel burning, you can call that as well. So all these components are all accommodated in the thermal energy, keep that in mind. So this is like 4 into 10 raised to the power 6, this is the kinetic energy component, that is 1.5 into 10 raised to the power 6, potential energy component is 2.1 into 10 raised to the power 6, and therefore we have to, so that is a good thing that we cannot calculate thermal energy as such, like practically, but we can do this rough calculation of other energies and get to know the thermal energy, right? So this is going to be 4 minus 1.5 minus 2.1, so that's like 3.6. So this is going to be 4 minus 3.6, that is 0.4 times 10 raised to the power 6, or you can write it as 4 into 10 raised to the power 5 joule. That is being lost in the form of thermal energy, right? There's no doubt about it. I think very easy, but all this is being done with the help of conservation of energy. You can grab a screenshot, then we move forward. Alright, next one. When a roller coaster is set in motion in the form of a high place, from a high place, its gravitational potential energy is converted to kinetic energy. Of course, we do know that you know, it's the roller coaster rising up and then it's getting converted to kinetic energy. How does the roller coaster first obtain its gravitational potential energy? So they are asking, how does the roller coaster first ride? So maybe it is some, you know, electric motor. It can be an electric motor which is driving the belt or the roller coaster up. It can be the chemical energy also of some battery. So there can be multiple answers to this, but mostly we can write electrical energy because majorly these are electrically driven, right? So we can write electrical energy or chemical energy of a battery can also be a possibility, right? So A part is electrical energy is converted to the gravitational. So they are asking how does, so we will write electrical energy is converted to gravitational potential energy, isn't it? Gravitational potential energy. Alright, next, since energy is conserved, why could the roller coaster not continue its motion perpetually? So they're asking that, you know, if there is no energy loss, like you talk about potential energy converting to kinetic, and then again, just like the pendulum case, where it can go on and on and on, but that's only possible if air resistance and friction is not there. But this is the problem, even with the roller coaster, friction and air resistance has to be there. So we would write, you know, why could the roller coaster not continue its motion? This is because some mechanical energy is converted to thermal energy, right? To thermal energy, which cannot be converted back to kinetic energy. So potential can convert to kinetic, kinetic can convert to potential, but thermal energy once gone, like once the energy is gone in the form of thermal, it can never come back, okay, in these kind of situation. Next, use a Sankey diagram to show how the principle of conservation of energy can be applied from launching station of the roller coaster to the highest starting position. Alright, so we will write that it is the electrical energy to start with, alright, or the chemical energy. So we will write electrical, or depending on whatever the mechanism is, electrical or chemical energy, right, that is being converted to first, let's say like this, then we can talk about like this, and then we can talk about like this, let's say like this. All right, so it can have three different components. We can talk about you know, it gaining potential energy, that is the main component. Of course, you know, this is not drawn to the scale, these should be a little thinner and this should be a little more thicker. All right, potential energy, okay, and then there can be a little bit of thermal energy being lost, okay, and then there can be kinetic energy as well. So they are asking, how does the draw a Sankey diagram from the launching station to the highest starting position. So there was a component of kinetic energy also, okay, assuming that it was set in motion. A small component can also be in sound energy, but we are assuming that it's almost like none of it. So this thermal energy is because of air particles and the you know, the rail particles as well, okay. But just to give you an idea that you can also draw the Sankey diagrams, the question might also ask you to draw an expected Sankey diagram. So that's how you have to do it. You have to divide or divert the energy into various components. Copy this down, then we move forward. Next, work. So now finally we talk about work. We have talked about energy very much now. So work is basically this transfer that we are doing. So you can take it as a transaction of energy. So whenever you are doing work, you are basically spending your energy and giving it to someone else. So if you're pushing a cart, you are consuming your food's chemical energy and you're providing kinetic energy to the cart, and that is what in physics work would mean. So like force is like effort in physics. When you apply force, you are doing an effort, expecting some displacement, and when that happens, that displacement causes work. So when force is accompanied with displacement, that is work for you. So in physics, work is done only when an object moves under the influence of a force. Mind you, it might not be the only force, there can be multiple forces there, so keep that in mind. But whenever force is accompanied with displacement, so if I would push this board and this board would not move, then I won't say the work is done. But if I push a cart and it moves, then I would say work is done. Okay. Work done by a constant force on an object is the product of force and the distance moved by the object. But obviously, we will talk about it. Work done is proportional to the force. More force you apply, more energy you spend. More displacement you cause, more work you do. And that is why work done we denote by W is equal to force times displacement, right? It is equals to the force times displacement. We will talk about this, but this thing here is what I want all of you to understand, that work is basically the change in energy, right? So if let's say if I am pushing the cart and if I have lost 20 joule of food's chemical energy, then that is very obvious that I have done 20 joule of work on the cart and that cart has gained 20 joule of kinetic energy. So whatever is this transaction of energy, that is delta E, that has happened, is basically the work done. Okay, keep that in mind, and there's nothing much to talk apart from this, just that the technical definition of work in physics, you know, because in general work can be anything, like even if you're thinking about something, that's work. That is the general definition of work. But in physics, that is not work. In physics, work is when force is accompanied with a displacement. Alright, so that's what we are writing here, that a force applied, S is the displacement, work done is equals to F times S. But keep one thing in mind, that what if there is another force F dash acting in the opposite direction? Then the work done by F is this, but the work done by F dash is going to be negative. Why would I say that? Because you know, it's just the opposite. This force was trying to push the ball when at position A to the left, but ultimately it moved to the right. So in a way, that's negative work for you. You know, it happens, like it's like backfiring. So you were thinking about something, you were putting in effort in that direction, but just the opposite happened. So that is like negative work. You were applying the force in the left direction, but the body moved to the right, then that is negative work for you. Keep that in mind. So if the force and displacement are in the same direction, then it is F times S. But if they are in the opposite direction, then the work done is going to be negative. The SI unit is going to be joule, and which is basically Newton into meter. But Newton into meter specifically is called joule, just to differentiate it from the moment of force. So if you remember, there also it was force times perpendicular distance for the moment of force, but there the unit was Newton meter. Here we will specifically call it as joule. Keep that in mind. So work and energy both have the same unit, because it is basically a change in energy, that is work. So you don't expect a new unit for work. It is going to be the same as that of energy. Alright, so a librarian pushes a trolley of books for shelving. The horizontal force F exerted by the librarian on the trolley is 20 Newton, and the trolley moves a distance of 66 meter in the direction of the force. Calculate the work done. Now you know this word here, in the direction of force, this is very important. This is very important, though we will talk about it in the upcoming classes. But for example, if something is being pushed horizontally, just to understand, and the weight is acting in the y direction, okay, while the displacement is happening in the x direction, then work done by the weight is going to be 0, because displacement in one direction and force acting in the perpendicular direction of that doesn't make sense. This force cannot cause this displacement. That is something we will learn with time, with more understanding of vectors. But right now I can just say that if there is a force which is acting perpendicular to the displacement, keep in mind this force has nothing to do with this displacement, and the work done by this force in causing this displacement is going to be 0. Okay, so that is why, you know, if you have this question, the cart is being pushed horizontally, and someone might ask you, what is the work done by gravity or the weight in this case? The answer should be 0. Okay, let's get back to the question. Calculate the work done on the trolley by the librarian. So I think it is easy. Work done is equals to force times displacement. Now the force is 20 Newton and the displacement is like 6 meter. So the answer is going to be 120 joules without a doubt, right? Explain what happened to the mechanical work done. So whatever mechanical work is done, whatever is the transfer of energy, it gets converted to it, or we can say, yeah, it gets converted to kinetic energy of the trolley. Kinetic energy of the trolley, isn't it? Easy? So keep this thing in mind. This was easy, but keep this thing in mind that whenever force is perpendicular to the displacement, you always call the work done by that force particularly 0. Alright, so now let's take the next one. The trolley of books of mass 30 kg pushed by the librarian in the previous problem reaches the bottom of a gentle incline with a certain speed. The vertical height of the incline is 0.5 meter. In order to maintain the same speed, the librarian exerts a force of 60 Newton to push the trolley over a distance of 4 meter. Alright, so this distance is 4 meter while this height that it gains is only 0.5 meter. Okay, calculate the work done by the 60 Newton force on the trolley along the incline. So no problems here. A part, work done is going to be force times displacement. Force is 60 Newton, displacement is 4 meter. So the answer is going to be 240 joules. No problems here. B part, calculate the gain in the gravitational potential energy. So we will write that's going to be mgh. Mass of the trolley is like 30 kg. Gravity has to be taken as 10 and height is 0.5 meter. Keep it in mind that this is not the height. Height is only what you gain in the y direction. So that's 0.5. So when you multiply this, this becomes 5 times 30, that is 150 joules. So you would say that if the librarian has done a work of 240, but still the trolley has only gained 150, kinetic energy is not changing. So there is some loss of energy, right? So there must be some friction, there must be some air resistance, and that is what you show in the Sankey diagram, that you know the chemical energy of the food that this librarian is spending, that is, mind you, 240 joule, is partly going in the form of definitely the potential energy, of course, the potential energy, and that is how much? That is like 150 joule, and the remaining energy that we have here, the remaining energy that is here is being lost in the form of thermal energy, isn't it? So this is the thermal energy that is due to the friction and the air resistance. So how much should that be? Of course it is 90 joule. So that's the Sankey diagram for you, that you have spent a chemical energy of 240 joule, and out of that it is dividing into these two components which you can clearly see. Alright, so you can copy this down. We'll take one more after this, maybe a couple more, whatever time permits, and then we will that will be all for this particular class. Alright, the next one, a crane lifts a crate upwards through a height of 15 meter. The lifting force provided by the crane is 6 kilonewton. How much work is done by the force? Okay, so then that's easy. Just that you have to calculate the work done, that is going to be force times displacement. Force is being applied in the y direction, it's being lifted. So force is 6000 or 6 kilonewton, and the displacement is like 15 meters. Okay, so 6 times 15 is like 90, and this is 1000, so this is like 90 kilojoules. Then they are saying how much energy is transferred to the crate. So if we assume that there is no air resistance, so this is again the problem. If air resistance is ignored, then you will have to say that entire energy of that has been transferred in the form of potential energy to the crate. But practically that does not happen. Some component is always lost in the form of thermal energy. But if we assume ideal situation, then that is the case. That's the gain in energy. Alright, so now let's take the next one. Suppose a cart of mass 2 kg is being pushed by applying a constant force of 30 Newton along a horizontal smooth surface. So this is a smooth surface, no air resistance to be taken into account. Calculate the work done during the period when the speed of the cart increases from 10 meter per second to 20 meter per second. Also calculate the change in kinetic energy of the cart during this time. Alright, so let's calculate the change in kinetic energy. That's going to be delta Ek, that's going to be K final minus K initial, final kinetic energy minus initial kinetic energy. That is half times mass, that is 2, times final velocity, that is 20 square, minus half times 2 times 10 square. So this is 400 minus 100, that is going to be 300 joule. Now the second part of this, to calculate, in fact the first part of this, to calculate the work done, we need the displacement first. What we need is the displacement. This is only for the extended students, that you should understand that there is this equation of motion that we have talked about, v square equals to u square plus 2as. Also at the same time using F is equals to ma. So force is 30 Newton, mass is like 2 kilogram. Using this, acceleration turns out to be 15 meter per second square. So I'm going to use this equation. Final velocity is 20 square, initial velocity is like 10 square, and acceleration is like 15. So let's use this to calculate the displacement first. So that's going to be 400 minus 100, that is 300 divided by 30, so that's going to be 10 meter. Now we are in the state to calculate the work done, because we have the force and we have the displacement. Again, I am repeating, you always have to pause the video and attempt the question first yourself, and only then you would enjoy the solution. Okay, so work done now is going to be force times displacement. Force is like 30 and displacement is like 10. So this gives us 300 joule. So now it is making sense that the surface is entirely smooth, and whatever work we have done has been converted to the kinetic energy, right? So I hope you were able to get a decent idea of things here. What do you mean by work done? What changes work causes? Whenever work is done, it always results in a change in energy or transfer of energy. So there was a lot that was talked about, but that's all for this particular video. We will come up with one more video of energy resources and all those stuff which are remaining from this particular unit. But that's all for this one. We will be coming up with the previous year questions as well, which is going to be the place where we will apply all the knowledge that we have gained out of these theory classes. Thank you very much everyone. See you in the next one. Bye bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.